hoping to do is to lead you down the rabbit hole, and then you will realize like there's a whole other world out there, and I think you'll never look at things the same way again. Okay, so here's the idea. So M is a proof of A. So let's go back to this. So this is the idea. Oh, so another way of saying it is that M thought of as an object can be say that it is of type A. Okay, it's just a question of, you can think of this program M via this idea, let me write PGM. The program M is of type A, or M is a proof of a proposition A. It doesn't matter. You can look at it either way. It's the same thing. Okay, so that's the idea. So what does this correspond to? Well, this also goes back to algorithmy, which I'm in the wrong page. I already scrolled, so I want to go here, which is the central idea of the notion of a variable. So one of the greatest achievements of intellectual achievements of human history is inventing the idea of a variable. And so what we're going to do here is we're going to use this notion of a variable. And the idea of a variable is, if I'm going to have an entailment that says something is a proof of A, on the assumption that I have a proof of A. Well, if you assume that you have something, but you only know about it, I assume I have an odd prime greater than 100. I don't know what it is exactly, but I know it's an odd prime, and I know it's greater than 100. Okay? So this is what the idea of a variable is for, so a variable object. So what you do is you say, well, rather than assume A is true, I will assume that I have a proof of A. Let's call it, give it a name, call it X. In a math book, it's usually parens 10.3, right? Okay? But we'll use a notation that is a little nicer, symbolic notation. So we'll use X, all right, which is a variable, just like you did in school. All right? And if X is assumed to be a proof of A, then it bloody well is a proof of A. And so we get this idea of the entailment, this idea that A true gives A true means that I can use a variable. And so that's the first thing. So this is the notion of variable. Now, what is the notion of a variable? Well, the notion of a variable is grossly abused in computer science. And so I'm going to insist, so this is another point in which I want to insist on being careful about our terminology, just as I was about provable. I want to insist that the idea of a variable, that thing that's called a variable in like almost any programming language that you can throw a stone at, okay, is not a variable. Okay? What is a variable is the thing you learned in school. Okay? You had it right when you were like 9 years old. Okay? And then somebody screwed you up. Okay? And I'm just saying you were right in the first place. So let's go back to like when you were 9 years old and what is the idea of a variable. I don't know about you, but when I first learned about variables, we used little geometric figures like box plus 3 is equal to 7. What goes in the box, you know? Okay, so this is what we're doing here with variables. And this is the invention of algorithmy. And I think also the ancient Hindu mathematicians, what is his name? Brahmagupta. Yes, am I right? Can somebody tell me? Is that right? Invented this notion of a variable. Okay? And so here's where I'm getting at, is I want to look at what this idea of transitivity is. Because what I'm getting at is the idea of plugging in. Okay? So what's going to happen here, now watch me screw my letters up again. So let's say, on the basis of an assumed but unknown proof of A, I can build a proof of B. And that's what the first line says. And on the basis of, let's call this one Y, I don't have to, but I will. On the basis of an unknown presumed proof of B, I have a proof of C. Then I want to combine these. On the basis of an unknown proof of A, I want to combine them in some way into a proof of C. And what do I do here? I plug in, if I got my letters right, what I'll call N for XM. And this is called substitution, or plugging in. For now, you'll get all of the details on this later. I sort of told you I'm waving my hands. The idea here is just like you did in school. You know, you have, did I mess it up? Every time I mess it up. Okay, I messed it up. M for XN, sorry. Transposing letters goes with the turf. I don't know what to tell you. Did I do it right now? Is that all right? No, I didn't. M for Y. Thanks. Okay, good. Yes. I just wanted to see if you were awake. Okay, so this is the plugging in that you did in school. You have a polynomial, and one of the, I think probably you enjoyed this when you were really young. Plugging in stuff and calculating, it's cool like hell, right? It's really fun. When you first think of algebra, you think, oh my God, that's amazing. So this is what we're doing, is we're just describing the process of plugging in. From a computer science point of view, what is the pedestrian term for this? In fact, there are Norton books written about this rule. What is it? What should it be called from a computer science point of view? Oh, boo! You better be able to tell me this. No, the notion of a variable, the idea of plugging in. What does it correspond to in sort of Norton book kind of stuff? O'Reilly books, whatever they're called, trade books. No, I can't hear. In a way, there's no functions involved, but you're on the right track. Really? Someone? Yes, link editing. This is called I'll call this the LD rule, just to be provocative about it, or link editing. The only thing a linkage editor is doing is performing substitution with the world's most grotesque syntax. Okay? .o files are some unbelievably arcane syntax, but what they're achieving is substitution. Okay? This is what is going on. Okay? So this I call the LD rule, just for fun. Okay? Like Unix LD. Okay? That's what is being done here. It's just substitution. Okay? And notice that, again, there's this kind of correspondence. So this in the middle now is mediating, you might say, between the proof theoretic side and the order theoretic side. And we have here, or eventually the category theoretic side. And this is the type theoretic view. So here the idea is that I'm doing the most rudimentary things about what are programs. Well, variables are programs, and I can plug one into another. I still haven't given you any honest-to-God programs, all right? So what I'm going to do is give you an honest-to-God program, okay? Okay, which I will do on this chart, which I will put in here. Well, this will be, these are usually called products or tuples, and we won't call them something else, but I could call them. Okay, so let's figure out what that must look like, okay? So we can look at this any old way we want. How about if I start here? All right, I'll start with this one. So let's look at what this means in terms of programs. It says, well, if given an x, which is of C, if you can give me an m, which is of A, I'm just like doing the thing here, right? And if you given a y, which is of C, in fact, I'm going to insist on calling it x. It's going to make my life easier if I do that. Then give me an n, which is a B. Okay. So if you have a proof of A from the lemma, if you have a proof of B from the same lemma, then on the basis of that lemma, you have a proof of A, and what's usually written cross or star or something, hash, and it depends on the language, okay, A times B. And what would that be? Well, what is the content of M and N? What is the content of this conjunction? It's the fact that they're both a proof of a conjunction ought to be two proofs, which we'll write as an ordered pair. And write it like that. And what is going on here is, if you assume a conjunction, then you can get the first conjunct by referring to it, let's say, first of x, and the second conjunct by, say, second of x, b. Oh, and then if I'm going to use a different notation, then there's a notational thing, right? One thing you do run into is there are established notational conventions in each independent field, and so when you're trying to make them all harmonize, you get into little creases. So it's not so common to use a wedge in a programming language, but you could. So I'll just write it as cross, okay? because that's the more usual way of doing it. And by the same token, it would be rather weird looking to write a meet as a cross, although you perfectly well could. It's just one of those things. There are different traditions that flowed together and then crashed into each other. Okay, so we have a notation that looks like that. Okay, so that's like the basic architecture. What is my time slot? Huh? Oh, okay, good. I'm in good shape. Okay, good. Usually there's a bottle of water. Is there water somewhere? Jim, where'd Jim go? I need some water. He's gone? Okay. Okay, so what was I saying? Okay, this is illustrative of the overall architecture. Okay, so this is what we're going to do. And this is going to be very richly developed. But now I want to get to a jumping off point, okay? And the jumping off point has to do with the equational properties of these proofs, okay? So the first thing I want to get across is the overall architecture, how these parts fit together, so that we have the notion of logic or proof theory, type theory, and category theory or preorders that we're writing over here, this kind of algebraic structure. And I wanted you to see the nice correspondence. Of course, I've shown you, oh, thank you, Frank. I've shown you the neatest, most straightforward, most direct case. There's a hell of a lot more to say about that, which we'll get started on in the next lecture. But before we, so let me just skip a few things in my notes because I would like to at least set up a particular problem. Oh, okay, yes, there's two things that I would like to set up with you. Give me a moment here. I have to think about what I want to do here. Frank, you're planning to talk about negation? Okay. Okay. So, all right. So what I would like to do now is to then let me just. I'll come back to that in a minute. So what I would like to do now is start talking a little bit, the beginnings, about equivalence of proofs, and this is where is the right jumping off point for me to talk about dependent types. That's why I needed this. This is partly to serve as an overview and partly to set up for what I need to talk about next. So the question I want to get at, and I'm going to begin looking at right now, is the idea, are when are two proofs equal? And let's write it like this. M is equal to N and A, which is expressing when are M and N, or just like the assertion is, are M and N express the same proof. This is what we're doing here. Okay, so we're going to have the notion of equality of proofs. So this is where we begin to get to the idea that proofs are mathematical objects. Okay, and one of the ways in which we express that idea is we talk about when two of them are equal. Okay, and what I want to set up now is the questions of equality and what is the notion of equality of proofs. This ends up being completely central to the theory of dependent types, which is why I am where I am. Okay? All right. With me so far? So what I'm going to do is I'm going to talk about, that's not the right spot, give me a moment. This is a more subtle issue than you might think. So what I want to do, let me check the terminology that I wrote down here. Ah, yes, okay, right. Okay. All right. Okay, before I do what I need to do next about equality, I need to introduce another concept, because it will help us a lot. Okay, so let's do this. So what I want to do is I want to introduce a distinction between what is called a synthetic judgment. You're going to see what the point of this is in a minute is, and an analytic judgment. And we've already have an example on the board. And an example on the board is when we say A is true. There's an example of what is called a synthetic judgment. This is the terminology versus what is called an analytic judgment. And the idea is, and this goes back to this point of having existential force, the key idea is that it requires evidence, which in the case of the judgment being true is a proof, okay, in this case. In other words, to correctly assert that a theorem is true, you have to have evidence for it. You say, oh, you say it's true. Well, then show me the proof. If you don't have the proof, well, you're just talking trash, and you haven't done anything. But to correctly assert that A is true requires evidence. You have to actually look to figure out what it means as some proof that something is true. And I want to contrast that with our other judgment, which is written MA here, which is called what is called an analytic judgment. And this is generally said to be, analytic could be said to mean it's self-evident. And what do I mean by that? And this is the traditional distinction between, in this particular domain, between proof search and proof checking. Okay? To determine whether A is true, I have to search for a proof. I mean, you can think of that as a mechanical procedure if you want, but you can also think of it as suffering, you know, over your desk, trying to figure out a proof of some assertion. Okay? So there's a process of search. And there's no getting around that. That's sort of a painful thing. Whereas this is the idea of checking. Okay? Checking a proof. And because if I say to you, not merely that A is true, but here's the proof, so that's the standard textbook format, is modulo syntax, M:A, that's what you get. You can compare the argument against the thing that it supposedly proves and check whether or not it's the case. Okay? So it's self-evident. In other words, it requires no further evidence, right? Nothing in addition to what is present in the judgment itself. So all the information you need is right there in front of you, and that's the information you use to do the check. Whereas here, the information you need, namely a proof, is not there in front of you. You have to find it. Okay? So that's the distinction between a synthetic and an analytic judgment. This is going to play a role in what I say about equivalence of proofs. Yeah. What's that again? The words. In this context, they were analyzed given by Martin Löf in a paper called what is the name of that paper? On the meanings of logical constants and the justification for the logical laws. That's one paper, and another one is called something about proof of a proposition, evidence for a judgment, something like this. I've forgotten what it's called right now. There's some papers of Martin Löf. I didn't have them in the front of my mind. We'll look them up. So there's some papers by, most of what I'm saying here is derived from Martin Löf, the Swedish mathematician, and his work is kind of derived from many sources, but I would say in particular the Dutch mathematician Brouwer, and is a very powerful influence on Martin Löf's work. In fact, you could look at Martin Löf as having really given full development of Brouwer's beginning ideas from the 1930s. Okay? Is that the answer you wanted?
That's interesting, and I also wonder whether there's what's synthetic about the first one and what's analytic about the second.
It's just the terminology that is used. Let me just say that. I mean, the terminology goes to Kant, right? And I don't know exactly. The why that particular choice of words off the top of my head. Okay, but yes, the reference point for this is margin left. Okay, so now in order to talk about dependent types at all, I have to talk about equivalence of proofs. So I want to talk about when are two proofs equal. And there are various notions. That's what's interesting. When are two proofs equal? And what do we mean by equality? That's another way of saying it is, what is equality proof? It's not so obvious. And it's not so obvious because, I mean, intrinsically it's not very obvious, I don't think, what the answer to this should be. And moreover, because the tradition in math has been to ignore proofs as being whatever it is we write down for some random reason, and they're not actual mathematical objects, nobody's really studied them very much. Okay? And so it's fallen to the subject of proof theory and computer science and category theory to give a full scientific study of what it means for two proofs to be the same. Okay? So what I want to do is to start out, I'm going to introduce kind of three kind of levels. And this is going to be very important by the time we get all finished, okay? By the time we're done, we'll be talking at the third level here, and I'll get to that in a minute. Okay, so the first one of which I will call is definitional equality. That's the terminology. Okay, that's just the term. And this is going to be an analytic judgment. And a lot of times people will use the notation triple bars, but to be perfectly honest, there's no real established conventions that are completely adhered to by everybody. So anything I write is always going to be a little not quite, nothing is standard. But there's kind of standard, okay? So the first thing that I want to talk about is definitional equality. So we're not used to these ideas, I don't think, unless you have experience in type theory. But if you don't have experience in type theory, you're probably not used to these distinctions. So now I have to do something that I have to take my time here because it's kind of tricky and might not look so familiar to you, and you're going to run into this when you start doing mechanizations, for example, in Calc. So it's going to be worth your while. You'll agree with me, yes? It's going to be worth your while to understand what I mean here. So this idea of definitional equality, I would call this sort of baseline. And there are different ways of explaining this. And one is, you can think of it as equality of sense, if you've ever run across that terminology. As distinct with what I'm going to do next, which I will call, I had to think of a word, and there's no standard word, so I called it denotational equality. We'll come back to that in a minute, which is it's going to turn out to be synthetic, and it's going to be equality of reference. This is the terminology I would like to get on the table. The distinction, this is Frege's distinction between sense and reference. Okay, so the famous example of Frege's is there's two. This is from natural, not particularly mathematical context. Is the morning star and the evening star. Both turn out to be the planet Venus, so they're not stars anyway. But they're called the morning star and the evening star. They have the same reference. They both refer to Venus. But they have a different sense. They carry a different meaning, a different information content. Okay? I don't want to give hours and hours of lectures on Frege's distinction between sense and reference. But I kind of hope you can feel, okay, that there is information content to how you pick out a number. Okay? So here's an example. I'll give you an example that I think is even more compelling. In the conventional treatments of logic, there are only two propositions in the world, true and false. Okay? So every single mathematical theorem either denotes, it refers to true or it refers to false. Okay? But obviously, so it means in particular all true theorems are equivalent. But obviously, right? I mean, yeah, that's obviously true in a way. But there's a vast difference in information content between the fundamental theorem of arithmetic and, let's say, the fundamental theorem of calculus, which are both true. Okay? They're both complicated ways of writing down the Boolean 1. Very complicated ways of writing them down that are vastly different. But you could say, oh, well, they're all just noise. It's just like big, fat, dust storm standing for true. Well, that's the conventional story. Why? Because the conventional story completely disregards sense, because the conventional story gives no pride of place in your theory to the proof itself. Okay? As soon as you bring the proof itself into the picture, you can sense, in an informal way, that this proof and that proof are pretty different things, even though they both stand for true. Okay? That is the idea. All right, so what we're going to be doing with definitional equalities, we're trying to get at this idea of equality of sense, whereas this denotational equality is going to be equality of reference. And then we're going to have an even weaker notion, which I will call equivalence, or weak equivalence, or homotopy equivalence, and we'll get to that. Okay, and this will also be a synthetic notion, and I will not say very much about that today, or I will just barely broach this subject. But by the time we get good and sophisticated in the course of these lectures, you'll be slinging this stuff around like you were born with it. Okay, so I'll show you how that all works. But let's start out with the real basics. So what do I mean by definitional equality or equality of sense? Even if I've given you that flavor, I still haven't pinned it down. I haven't defined exactly what it is. So I'll give you a little bit of example, and this is the kind of thing that Frank is going to develop in a lot of detail. And the example is going to be derived from what I have on the board here. The idea is this. It's most easy to explain. The discussion can be had on either this side or over here, but it's best to work at it. It's notationally the most convenient to work with the type theoretic notation. So that's why I've set it up the way it is now. Okay, because I want the proofs to be objects, so I've got them. Okay. So an example of this is is the composition. So the idea is, suppose I compose this rule with that rule. What does it mean to compose those two rules? It means to perform the substitution, which I have above the board here. So suppose this is my m, okay, that I have in mind. This is the overall m up here. And I'm going to plug it into the n. The n is first of x. So if I plug this term, which is a cross b, for this variable, which is a cross b, in this expression, m for y, I wrote it there, m for y n, then what do I get? Well, if I compose those two, I will get first of mn will be a proof of A, under the assumptions that this is a proof of A and this is a proof of B. Right? If you work it out, right? Do you see that? If you take this rule and that rule and use the principle of substitution, which I described here, and you put those two together, you will get this compound expression, because this is substitute the pair mn for x in the expression first of x. And if you calculate that out by hand-wavy rules that I haven't specified, but plug it in, you'll get that. Okay? So now, here's the thing. You can think of this in many different ways. One way to think of it is a principle of proof. I proved this is A and B. So I proved A and B, and then I turned right around and said, therefore A. So obviously it's a little strange, because I prove A, I prove B, and then I say, oh, and you know what? Therefore A after all. And you say, oh, you say, okay, excuse me. Okay, I can't object to that. But it's sort of a cockamamie proof. And the reason is, and let me make room here, you might as well say that this is just as equivalent to M. That is, why not just simplify that? I mean, you kind of went all the way around the barn here. You proved two things in order to extract out the first thing you proved. Well, the hell with the N. Just forget about the whole business and just simplify it to be that. And by a similar line of reasoning, you can say, well, you proved two things, and then you turned right around and pulled one out of it. So why not just prove the second thing and be done with it and don't bother with the first? And so we get this equivalence. So these two principles are kind of a starting point, okay, for talking about a notion of equality of proofs. And these are called definitional equalities, okay? Another way to think of this is that, or equality of sense, we can also think of this as, to use computer science terminology, we can think of it as symbolic execution. And this is kind of what you learned in high school algebra. Your notion of calculation involved, for example, plugging in numbers for variables and then applying the rules of arithmetic. You take x squared plus 2x plus 1, you put in 7, 7 times 7 is 49, etc., and you do the arithmetic and you get your result. So there's an execution model there. That is, when people were teaching you algebra, unfortunately they didn't, I'm pretty sure they didn't bring this out for you, but what they were doing is they were teaching you a programming language. And in fact, all programming languages, done properly, are just big-ass generalized polynomials, okay? That's what's going on here. That's the idea of it. I'm just going to generalize this idea of computing by calculation. If you do that, then you get these beautiful correspondences, okay, which go on and on and on and on. And everything is really nice. So that's the thing that sort of the whole point of the summer school. Okay, so these are two principles of proof of definitional equivalence. What are some other principles of definitional equivalence? Well, the ones that I kind of took for granted without even saying is it ought to be an equivalence relation. So let's just write RST here, and that will be true for all of these. These are all supposed to be equivalence relations. So clearly, whatever your notion of definitional equality is, it ought to be an equivalence relation. Every proof is equal to itself, symmetrically and transitively. That makes perfect sense, okay? Plus, we can add in, these are called, the generic term for this is sort of beta-like rules. That's, you'll see why a little bit later if that terminology doesn't appeal to you, it will after you learn a little bit more. Okay? These are the symbolic execution rules. This is symbolic execution. You can think, I don't like that word, but people use it a lot. I mean, there is no other form of execution besides I don't know what the hell they're talking about, but I know that people usually say that, so I'll say it, okay? All right, okay. So that's first and second. Now, the other interesting thing is you would expect it to be what is called a congruence. Congruence properties. So, for example, if M and M prime are the same proof of, let's say, a conjunction or product, then first of M and first of M prime ought to be the same proof. And similarly for second. So we would write second, and B here. We would have principles of congruence like that. And moreover, we would expect to have further principles of congruence. Like, if M is the same as M prime, and if N is the same as N prime, then the pairs Mn and M prime N prime ought to be the same. So that's did I get it right? Yeah. That ought to be the same. Okay? Those should be the same proof. So we have, these are called congruence principles. Okay? It can replace equals by equals anywhere you see it. Okay? So we should certainly have that. And now an interesting question comes up. So are you with me so far? Okay? Because without these rules, there's no obvious, don't jump to conclusions. If I didn't put these rules in specifically, there would be no reason to think that they hold. Okay? I want you to see that. If you just say, these equations hold plus it's an equivalence relation, it does not imply that you can replace equals by equals anywhere. It's an additional condition. Okay? And another way of saying it is that, this is a slogan-y way to say it, all operators respect definitional equivalence. Okay? That's an idea. Okay. So that's the meaning of these congruence rules. So first and second, as operators, respect definitional equivalence, meaning if you give them equivalent arguments, they give you equivalent results. And the same here for the pairing operator. Okay, now I want to draw the distinction between, and then I'll finish, between definitional equality and this, what I'll call denotational equality. In order to do this, I need to wave my hands a little bit again, because it's just a question of the timing of the lecture. So everything will come out in due course, but I have to like a little bit fudge because you know, you got to do something to get started. Okay. So here's the example that I want you to understand. This next example is of the utmost importance to everything you're going to do the rest of the time you're here, particularly with your mechanizations, and it's going to drive you crazy. Okay? So let's watch. So this example is a little out of band. It's not material I've developed yet. Okay? We'll develop the appropriate material shortly. But here is the idea. So let's say we define addition by recursion equations as follows. Somewhere else, somebody must have done this. They'll say a plus 0 is equal to a, and they'll say a plus, you know, the successor of b is the successor of a plus b. So these are 0 and successor for generating the natural numbers. This is a very simple way of doing it. Okay, but let's just say we define addition in this manner. So this is our definition. Okay, this is how we define it. So this is the definition of addition on n, natural numbers which are generated by 0 and successor. Okay, so here's the thing that I want to show you that's important. Okay, are you with me so far? I want to distinguish equality of sense and equality of reference. So here is the idea.